Okay, you guys, so I thought I would take some time to more slowly go through some of this ionic nomenclature practice. This is just a beast of a topic, okay? I know it is a lot, and I know I have given you a lot of practice. I've given you 2 pages front and back. The way the pages work is it scaffolds so nicely. This first page, number 1, is the easiest of the ionic compounds. On the back of that page, you have page number 2, and it's ionic structure or ionic naming, but with, oh my gosh, you guys, my polyatomic ions, okay? And then the third page is like, oh no, she's throwing some transition metals into the mix. And yes, I am. We got some transition metals to take care of. And then finally, on the back of that, we've got just a mix of everything. So you're going to have to apply all of these rules, which is going to be a little bit scary at first, but also kind of a little bit fun. We made this cute little nomenclature booklet. If we get stuck, we're totally going to be referring to the little cheat sheet rules underneath the little doors here, okay? So this gives you a walkthrough on how to name ionic compounds. Any type, polyatomic ions, transition metals, anything. The directions on here will help you. And then under here, we have some directions on how to write formulas for those ionic compounds. So we're going to have this next to us as our little bit of a security blanket because it's going to be very helpful. Remember, on the back, we do have our list of polyatomic ions. If you'd like to use your larger chart that I gave y'all at the beginning of this unit, and maybe a little bit kinder on your eyeballs because that hurts my eyeballs for sure. And then, of course, our periodic table that we've colored to make us feel nice, warm, and fuzzy. And we've got our valence electrons and oxidation numbers all ready to go. Okay, that was a lot of talking. I'm so ready to do this right now with you guys. Yes, okay, so we're going to zoom in. Okay, write the formulas for the following ionic compounds. So we are doing writing formulas. First of all, I want to check and see if, Sabaka is not trying to trip me up and she's giving me something besides ionic compounds on this page. The way you check, and I've got my red and blue colored pencil, is in an ionic compound, we know we have a metal and then a non-metal. The metal is always written first. Let's check on the first few one of these just to make sure I'm not being sneaky. Beryllium, he better be a metal. Y'all, he is. Oh my gosh, to make myself feel nice and warm and cozy, I'm totally going to put a line underneath him. That's a metal. And then phosphide. Alrighty, y'all are like, what a phosphide. What you're going to see in all of these names is an IDE ending. Ide. That is me saying that an element who does not end in ide has now had an I put on the ending just to let you know that that element is in an ionic bond. So phosphide is actually phosphorus. And phosphorus totally is a nonmetal. And we can do these for the first few one of these. Lithium, is he a metal? Yup. I'm already on the metal side, so let's bounce on down. Magnesium, he's totally a metal. Sodium, a metal. Barium, where's barium? Yeah, he's right down there. Totally a metal. Y'all, I have not checked you. So far, we're looking good, but let's check that make sure the last one of these are non-metals. Nitride. That's nitrogen. Nitrogen is totally a non-metal. Oxide, oxygen. Nitride again, nitrogen. Arsenide, what is she doing here? Y'all, that's arsenic. You're like, oh my gosh, we have never used arsenic before. Well, we're using him now, and he's a non-metal, so do not worry. Okay, it looks like for each one of these, we do not have to do the red and the blue for every single one, but I wanted to visually show you guys that this is a metal and a non-metal. If you'll notice, the metals are always written first, okay? All right, so now we are ready to write formulas for these ionic compounds. We do have a little book, and the little book's gonna help us out. At the top of the page where it says ionic writing formulas, it says crisscross. We're like, what does that even mean? It says write the symbols for the ions with their oxidation numbers. And then if you need to, you're gonna use parentheses around your polyatomic ions. We do not have polyatomic ions, thank goodness. So I got to write my symbols for my ions with their oxidation numbers. Well, how am I going to figure out the oxidation numbers? Y'all, is where they are on the periodic table. So my first guy, we got beryllium coming in hot. So beryllium is we've got Be, and his charge is a +2 charge. Y'all, I'm sorry, my guinea pigs are losing their minds. They're hungry. Hopefully they will calm down. And then phosphorus is group 15 with a -3 charge. So -3, okay? All right, so we have done that. What is my next direction here? Let's see. It says crisscross. Now, that is not a very clear thing, but we will be doing crisscrossing all the time to where whenever you see crisscross, you will know exactly what I mean. So that means you're actually going to take the numbers of the oxidation numbers, not the positives or negatives, and those are going to get crisscrossed down as subscripts of the opposite ion. So what that means is that beryllium's 2 is going to slam down and be underneath the phosphorus. And that phosphorus's 3 is going to slam down and be underneath the beryllium. So the formula for beryllium phosphide is Be3P2. And you're all like, oh, what is going on with that? You guys remember when we did this activity not too long ago? And we kind of mapped out how many of each ion you needed to complete each one's octet. And some of them had like, it wasn't like a 1-to-1 ratio. Like this was 2 iodines for every 1 beryllium. And this was this situation. This was this situation. What we just did here on this page was not having to do all of this to figure out what the formula is. Okay, so the theme here is I've crisscrossed those charges down, which is super exciting. Okay, and I'm going to actually write this off to the side because I feel like I do not have a lot of space up here on top of my examples. Okay, let's do the next one. Lithium. Lithium, group 1. So lithium has a +1 charge. And then I have nitride. We said that was nitrogen. Nitrogen is in group 15. He's got a -3 charge. Yes? So we crisscross just the numbers down, which means that nitrogen gives that big old 3 to lithium. And lithium gives a 1 to nitrogen. Now, if you have a 1 being dropped down, a 1 we do not write because it is understood if you write that element symbol, I am giving you that there is 1. So we have Li3N. That's the symbol or the formula for lithium nitride. Ooh, I didn't talk about the very last one. The very last rule. Sorry, we haven't needed it yet. But here's the case where if the ratios or the subscripts that you have created from it drop down, if you can reduce them, you will reduce them if needed. When we get to an example like that, then we will kind of break that down a little bit further. But that's all it is for writing ionic formulas. Okay, you guys. So here we go. Ooh, I'm excited. Okay, next one, magnesium oxide. Oh, speaking of reducing subscripts, I'm getting excited. So magnesium, he's in group 2, so he forms an ion with a +2 charge. And then oxygen, group 16, forms an ion with a -2 charge. So each guy is dropping down a 2 from the crisscross to where this is what we get. We get Mg2O2. This would be me saying, do I still have my page? Let me still have my page. Yes. If I were to draw one of these guys, that would be me having like 2 magnesiums and 2 oxygens. Isn't that the same thing? A 2-to-2 ratio, the same thing as a 1-to-1 ratio? It is. So that means I get to reduce the ratios if I can, which means you find a common number that you can divide both of the original numbers by. So my formula is MgO. You're like, but I thought there were 2 oxygens and there are 2 magnesiums. Guys, keep in mind, in an ionic compound, it is just a giant crystal lattice structure. And I know I keep referring back to this thing of a bunch of these, a bunch of them. This is just showing what the ratio is. If I had a giant crystal of beryllium iodide, you guys, for every 1 beryllium ion, I'm going to have 2 iodide ions. And there's bazillions of them. I'm just looking for the ratio. That's what these formulas are. It's the lowest whole number ratio. So my ratio for magnesiums to oxygen, even though it was like a 2-2, that's just 1-to-1 for him. That was a big tangent, but that's why you're watching this video, because you need me to explain a lot more. Okay, moving on. Next one. We're going to do sodium nitride. Okay, sodium nitride. Okay, sodium is in group 1. He's got a +1 charge. And then nitride is nitrogen. We've used him, nitrogen. So he's got a -3 charge. So crisscrossing those numbers down, I have Na3N. That's sodium nitride. Okay. Now, if you need to set up your crisscross like this every single time, that is totally fine. I'm going to show you another option. Pretty soon you'll get to the point to where you can just look at the name and be like in your head, crisscross it down, you'll know the formula. But this is like my next incremental step as I'm starting to feel a little bit more comfortable of what I do instead. So barium, I'm like, cool, where is barium? Oh my gosh, he's right there in group 2. I'm like, well, he makes a +2 charge. I just write the +2 above him. And then arsenide, oh my gosh, a little bit of a sneaky one. He's in group 15. He's got a -3 charge. So I've written the charges above each one of the ions. And now I can, in my head, be like, swap your numbers down. Which means barium, his symbol, he's going to get the 3 from arsenic. And then arsenic, which is AS, is going to get the 2 from barium. Another thing to keep in mind, you guys, is that these ionic compounds, they're going to be overall neutral. That is the reason why we're doing these subscript things. That is, I keep pulling this paper back out. That is the reason why we figured out how many of each ion we needed. In order for everybody's valence electrons to be accepted by whoever they needed to be, we did that so that everybody's charge would be neutral. If you notice here, like on this example, we had 2 +1 lithium ions, which means we only needed 1 -2 oxygen ions, right? So the charges overall cancel out. So if I look at a formula, my formula is telling me the same thing. I had barium. Barium has a +2 charge. Well, if I have 3 of them, my overall positive charge coming from the barium is 2 times 3, a +6 from him. Now my arsenic, I had 2 of him, and each one of those guys had a -3 charge. So 2 times a -3, a -6. +6 overall and a -6 overall. That's where that ionic compound becomes neutral. Ooh, this is getting good. Okay, I'm going to zip on down here and do a few problems with the naming, meaning I've given you a formula and I just need you to name things to make sure I'm not trying to trick you up. Let's see if she's given me, in fact, a metal and a non-metal for each one of these, because that is what an ionic compound is. Okay, looking up here, I've got magnesium. Yep, that's metal. She gave me a metal first. Looks good so far. Let's zip on down and do all the metals. Calcium, totally a metal. Lithium, totally a metal. Beryllium, a metal. Aluminum, he's over here. Don't you worry, he's a metal. Cool. Now the second element better be a non-metal. Bromine. Let's see, bromine, where you at? Right there, a non-metal. Good, so I'm going to underline him in blue. Sulfur, yep, non-metal. Oxygen, yep, non-metal. Sulfur again, non-metal. And then fluorine, non-metal. Okay, cool, looking good. I got a metal and a non-metal. We're ready to roll. Let's grab our little nomenclature booklet and see if our little door that tells us how to name things in ionic compounds is going to be helpful for us. Okay. Whoa, I see a heading way up at the top. No Greek prefixes. You're like, I have no idea what she is talking for. This is for later when we talk about covalent bonding. They have different sets of rules. And I just wanted to remind you that when we get into covalent bonding, this is going to be a statement that you will probably need to see a few times because you will want to try to give them prefixes. You know, like what is she even talking about? Okay, the first step is we name the cation, the metal. It says group 1, group 2, silver, zinc, or aluminum, or ammonium, that positive polyatomic ion. If I have those, I just use the element's name. Okay, let's see for the first one. I got magnesium. Where is magnesium at? He's in group 2. So they're saying if I am any one of these, yeah, I'm group 2. So they're saying just use the element's name. Okay, he's magnesium, so I will write magnesium. Magnesium. Cool, okay, yes, amazing. I know there's some other suggestions on how I can name the cation if we are something different like a transition metal. You're like, oh no, we're not doing that just yet. But we've named our metal cation. We are good. Now we're ready to part 2, name the anion, the non-metal. They're giving me a couple of options here. Single element or a polyatomic ion. Let's see what I got. Am I a single element? Yeah, I'm a bromine. So it says just use the element's name with an IDE ending. So I'm gonna use the name of sulfur, but change the ending to ide, which is gonna not sulfur, bromine, but change the ending to ide, which is going to be bromide. So this is magnesium bromide. which is very fun. Okay, see the next one. We got calcium. Calcium. He's a group 1, group 2, silver, aluminum, or zinc. So we just named calcium. And then we got sulfur. He's a single free element from the periodic table. So we got sulfide. Next one, that's lithium. And the second element in there is oxygen. So oxide. Look at this. I'm just naming 2 things that I see. No thinking required by me. Okay, we got beryllium. Sulfide. We got aluminum. Fluoride. You were like, that is so easy. She was scaring me with saying how hard this stuff is. Yes, this is very, very, very easy. You get excited when you just see 2 elements off of the periodic table for you to name. Notice how I kind of glossed over that some of these guys had some subscript numbers. I did not represent that at all in my naming. You're like, well, how was I to know? Like, how were you supposed to know that? I wanted you to know that bromine has a 2. Guys, we just worked stuff like that up here, okay? We need the crisscross. From a crisscross, that's where that 2 came from. And in fact, if you want to kind of think about it, like, okay, well, we know that magnesium, he's got a +2 charge, thank you for being in group 2, and a bromine's got a -1 charge for being a halogen. Oh, from the crisscross, there has to be 2 bromines, 2 -1 charged things to neutralize or cancel out that 1 magnesium who's got a +2 charge. That's where those numbers come from. I do not have to freak out about that when I'm naming. I just write the things that I see. Great. So there's some fun stuff for you to chew through. I thought I would bounce down here and look at some of this fun chartsy chart. There's a little, I forget the name of the puzzle things, but you basically combine everything that's in the same row in the column. Okay, so here it says, write the formulas for the following cation and anion combinations. So here I have some, are these cations or anions? Let's see, bromide, oxide, iodide. Oh, these are my non-metals, so these are my anions, the ones who form negative charges. And then these guys, potassium, strontium, cesium, aluminum. Yup, these are totally my metals, my cations. So what we can actually do here on this chart first is I like to, in the headers, go ahead and write the charges of those elements anyway. Because we know when I'm writing my formula in the boxes of whatever combination I'm giving you, that charge is going to help me out for the crisscross, knowing what number I have to drop down. Okay, so bromide is bromine. He is right there. He's got a -1 charge, right? And then we got oxide. Oxide is in group 16. He makes a -2 charge. And then iodide, group 17. He's a halogen, -1. Selenide, you were like, what is going on even with that? Selenide is selenium. Selenide. He's in group 16. He's got a -2. Then we got a phosphide. Phosphorus. He's got a -3. And then carbide, you were like, what is that? Carbide. Oh my gosh, you guys. Carbide is actually carbon. And you're like, wait a minute, a +4. Y'all, it is not very common that carbon ionic bonds, but it can. So I know I had you guys memorize a +4, but if you want, it can potentially be a -4. We talked about this before. That 4 represents what it needs to do in order to get its octet. When we did a +4, that meant he was losing his 4 valence electrons. He can, with kind of a similar amount of ease, gain 4 electrons to satisfy his octet. He has that option. The main thing here is that we know he's going to be an anion in this combination because everybody up here is an anion. So we're going to give him a -4 charge. This will not be a very common situation for you to do carbide. In fact, I feel like next year I may just want to like cancel out that chart because it may confuse you guys more than y'all need to be. Okay. All right, we got metals here. I'm going to go real quick. So we got potassium, group 1, +1. Strontium, group 2, +2. Cesium, group 1, +1. Aluminum, group 13. We know he is a +3. Zinc. Huh? Remember when we wrote this on our periodic table, +1, +2, +3? That's because zinc always has a +2 charge. So from now on, if I give you zinc, you're like, yep, he's got a +2. For the other transition metals and the guys underneath the stairs here besides aluminum, you don't know what their charge has to be. It can change or it can vary. But zinc, we always know he has a +2. Speaking of silver, he's always got a +1. Now, this is a little bit of a preview into where we're going with this. Here I've given you a transition metal. I've given you iron. You're like, great, he's not in one of my groups. Sabaka told me to like hold off on that. And yes, this is how I will let you know what charge any one of my transition metals, meaning somebody who is not in group 1, not in group 2, not silver, zinc, or aluminum. This is how I'll let you know anybody else what their charge is. So I give you this Roman numeral thing in parentheses. This means that this iron forms an ion with a +2 charge. Okay? And this iron forms an ion with a +3. You're also probably like, well, how do you know it's plus and not minus? Well, they're metals, right? Metals. I've colored them red, which means that metals, and in fact, we can write this on here, they lose electrons. This is a smart idea. Look at me being smart. Yeah, positive. And then we can also write for our metals, our non-metals, we can write gain electrons, and they can be negative. Perfect. I love that. So it's going to be a positive. Okay, so now what we're going to do is we're going to combo this up, and we're going to pretend these charges get dropped down, crisscrossed down, and that'll represent the subscripts that will relate the ratio of each ion that you need in order for the atom to be neutral, or in order for the compound to end up being neutral. So potassium and bromine, a 1-to-1. That means you drop it down, you're going to have ones there. So it's a 1-to-1 ratio between the potassium and the bromine atoms, or ions here. But here's the trick. Do remember up here, we always wrote the metal first, which means, oh my gosh, I'm going to get my colored pencils out again. We're going to write my metals first, okay? And here's my non-metals, yeah? So my potassium goes first, and my bromine goes second. The crisscross down is a 1-to-1 ratio, so it would be K1, Br1. Let's do one that's a little bit trickier. So this is between strontium and bromine. So I know I'm going to have Sr going first because he's the metal, and then bromide is Br. Now I left a little bit of space because I don't know what my crisscross charges down are going to be, but it looks like strontium is going to slam a 2 down onto the bromine. And my bromine's going to put a 1 down onto the strontium. So my formula is SrBr2. I'm going to zip on down and do aluminum and bromine. So aluminum, Al, bromine, Br. Aluminum's going to slam a 3 down onto the bromine. Bromine's going to slam a 1. So we have AlBr3. Yes? Basically, the way we work this is we just start slamming things down, yeah? We take the numbers. We do not take the positives and negatives. We are just trying to figure out how many of each ion I need to neutralize the positive and negative charge to end up being 0. Let's bounce over here, and I want to do a couple with the oxygen one. So let's pair up oxygen with potassium. Potassium has to be written first, so it's going to be K something, O something, right? Now I crisscross down. Ooh, that oxygen's gonna, boom. He's got a 2 down there on that potassium, right? And potassium, he's gonna put a 1 down there. So the formula for potassium oxide is K2O. Let's do this one. Strontium has to go first. He's my metal. Oxygen goes second. Let's think about this. 2 and 2, boom. A 2-to-2 ratio. A 2-to-2 ratio. Can I reduce that down? I can. A 2-to-2 ratio is the exact same thing as a 1-to-1 ratio. If I take both those 2's, I can say, yeah, I can divide both of those 2's by 2 to get to a 1. Let's do aluminum and oxygen. Aluminum has to be written first, and oxygen is written second. Let's see how many I need of each, how many of each I need. Oxygen is going to put a 2 down underneath aluminum, and aluminum is going to put a 3 down underneath oxygen. So these are your formulas for some basic, simple ionic compounds. It is all about the crisscross, yeah? And it is all about just naming the two things you see, the metal's name and the non-metal's name, just making sure that ending is turned into "-ide."